Our first speaker is Young-Hyo Park, who will present his position paper on automatic environment shaping as the next frontier in reinforcement learning. The stage is all yours. Thank you.
Hello, everyone. Thank you for being here. My name is Young-Hyo Park, and I'm excited to present our position, Automatic Environment Shaping is the Next Frontier in RL. This is a joint work with my colleague Gabe and Polkett from the Improbable AI group at MIT. To give you some context before we start, me and Gabe both come from a robotics background. And as a grad student working on robotics, I always dream about a magical box that can automatically create a robotic controller for me by simply specifying the robot, environment, and task I want. And I call this magical box Automatic Behavior Generator. And before we move on, I want to emphasize the word automatic here. It means that this box should only be powered by time and compute, not by human effort. This magical box, if realized, will serve as a core tool, enabling robots to autonomously generate behaviors on the fly, even after its deployment to people's houses. But I want to ask you all, do you think we're being a bit overly ambitious? Is our dream, this magical box, too good to be true? Well, if you think about it, this is what reinforcement learning is promising us in some sense. Reinforcement learning in theory is a general purpose, automated, optimal control solver that can produce working controllers for any MDP setting. However, from a practical viewpoint, who's trying to use RL as a tool to train robots, this claim is not necessarily true. Although RL itself does not require human effort during its training process, we want to point out that there is a very heuristic, labor-intensive process that are required to make RL work in practice. And that is what we call environment shaping. When an RL algorithm fails to find a solution in practical scenarios, between the choice of fixing the RL algorithm and shaping the environment to make it work, practitioners typically tend to choose the latter. The core problem of such practice is that it heavily relies on human effort. Domain knowledge for the task, intuition, and sometimes a bit of luck is crucial to get things right. A very well-studied example of environment shaping that you might all already know about is the reward shaping problem. We all know that RL agents love to hack the reward when they can, so engineers typically go through the process of shaping the reward to prevent it. In fact, I would say that this is the biggest reason why some people in our community hate RL so much. And I completely understand the process of reward shaping. It's definitely not fun to do. Unfortunately, I want to point out today that reward is not the only thing that we usually shape. Robotics engineers carefully shape nearly every component of the environment to make RL work in practice. And again, the only optimizer that is currently known to work the best for this problem is graduate student descent, a process entirely relying on human effort. All those being said, what am I arguing today? First, I argue that the community should start prioritizing research to automate the heuristic process of environment shaping. At the same time, we also need better RL algorithms that doesn't require heuristic environment shaping in the first place. And to do that, I argue that we should be benchmarking our RL algorithms on unshaped environments without any task-specific heuristics included. To better back up our argument, from now on, I'll try to give you some examples of the heavy heuristics that are involved in popular robotics RL environments, and show how crucial they are to make RL work. As an exemplary environment to analyze, we chose ICML, one of the modern benchmark environment containing diverse robotics tasks. Let's first talk about action space shaping. In the context of robotics, action space shaping is a process of choosing how to convert the action predicted by the policy to an actual command that can be sent to the motor. An unshaped action space will thus look very simple. We are just letting the policy to directly predict feasible motor commands. However, most RL environments apply a bunch of task-specific heuristics to shape the policy outputs before it gets passed into the motor. This example code you just saw, for instance, applies diverse scaling, clamping, moving average filters, and PD controller at the end to finally convert the policy outputs to motor commands. The problem of this kind of shaping process is that it not only is very task-specific, but it also introduces a bunch of extra knobs and hyperparameters to tune. Unfortunately, this action space shaping is a necessary evil for RL algorithms. We have tested that PPO, for instance, completely fails to solve these tasks if we remove such shaping. And our findings are similar for observation space as well. Observation space shaping is basically a feature engineering problem, selecting the relevant states from what's available from the simulation to create an observation for the policy. For instance, for the task of opening the door using a manipulator, an unshaped observation space will be a simple concatenation of every raw simulation states that are available. However, typical RL environments go far beyond the simple concatenation. They introduce multiple hand-engineered task-specific terms, and they often convert certain states with unique properties, like rotations, to a different representation that are known to be better for neural networks to process. And such processes are also very crucial to make RL algorithms work in practice. We can break the RL by just removing those handcrafted terms from the observation. Although I'm skipping the other examples of environment shaping due to time constraint, you can take a look at our paper for more comprehensive examples. Now that we learned about the details of environment shaping and how it affects the RL performance, let's talk about how we can automate this environment shaping process. Automating environment shaping is a challenging problem for many reasons. One of the major problems is that there is no compact way of parameterizing the vastly diverse ways of doing environment shaping. If we assume a fixed functional form for everything, we can try extracting the coefficients and do some classical hyperparameter optimization on top of it. But this is a very limiting way of representing the shaping functions. Therefore, people have recently started to think about a more flexible way of representing the shaping operators. One of them is to use Python code itself as a way of representing these functions. This allows us to view environment shaping as a code optimization problem using large language models. This paper, called Eureka, is a good example of using large language models as a sampling-based optimizer to automate the real shaping process. So we have conducted some experiments to see whether the proposed automation method using LLMs can be extended to other shaping components. And as you can see over here, models like GPT-4 was able to successfully shape action and observation space with similar to human performance. However, interestingly, when we asked GPT to shape multiple components jointly at the same time, the performance dropped dramatically. And this can be a critical problem since our experimental findings suggest that optimizing individual components one by one in a sequential manner often leads us to locally optimal performance. All that being said, I believe we still have a long way to go to fully automate the process of environment shaping. Now that we have discussed all the aspects of environment shaping, let's discuss about path forward. Recall that I was advocating for the research focused on either automating the environment shaping or developing better RL algorithms. To support both direction of research, we have created a code base, which basically contains a collection of unshaped robotics environments that people can test their RL algorithms on, with nice little APIs and tools to facilitate the research of automating environment shaping. And before I wrap up my talk, I want to discuss about possible counterarguments that people might have against ours. Going back to the beginning of my talk, I shared about the dream I have, creating a magical box that can automatically generate closed-loop controllers for robots. And then I kind of implied that reinforcement learning will be powering this magical box in the future. However, I think some people might disagree with this, especially considering the resurging popularity of doing manual data collection and imitation learning. Some people might think that our dream of magical box will be realized not by automating RL, but by training some huge foundation model that consumes all these data sets collected by all these companies. However, I still believe in the power of RL as a tool to generate robust, generalizable, and especially superhuman behaviors that cannot be easily achieved with imitation learning. And also, the behaviors generated by RL pipelines can also be used to train those foundation models as well. Therefore, I argue that making RL easier to use will enable a virtuous data cycle for training better embodied intelligence. And with that, I would like to wrap up my talk today, and I'm happy to engage in exciting discussions about our patient. Thank you.